Alright, so in this video we go over section 8.3 maxima and minima of functions of several variables, in which we are going to determine critical numbers and then introduce the test that we will use to determine whether we are going to have a relative extrema, such a max or min or saddle point, which we will describe later in the section. Well, before moving on to the the multivariable case, it would be a good idea to do a little refresh of Math 121. What's the process to determine um, the coordinates in which a given function has any relative extrema, such as max or min, inflection points, if any, and intervals in which the function increases or decreases, and where it's concave up or down. And then, well, we're going to use all that information to sketch a rough sketch of the graph. Of course, if you look at this, it's going to be a polynomial. It's not going to be something really hard to graph by plotting points or looking at up to your graphing calculator. Alright, so let's have a look. So the first thing we do is take the first derivative, f prime of x, which is 6x squared minus 6x minus 12. So once we find the first derivative, we are going to use the first derivative test to determine the intervals in which the function increases or decreases, and then find relative max or min. Okay, so what we do in this case is to set the first derivative equals to 0 and solve the equation for x. In this case, well, you don't want to do the diamond method to factor this trinomial, rather reduce the coefficients because they're all divisible by 5. So we're going to have to x squared minus x minus 2 equals to 0, which is nicely factorable. Alright, so factors of negative 2 that add up to negative 1, negative 2 and plus 1 are the factors. And because negative 2 times 1 is negative 2, and negative 2 plus 1 is negative 1. So from here we get x equals to positive 2 and x equals to negative 1. Now, what about these numbers? So these are going to be our critical numbers. So I'm going to draw a number line, and I'm going to locate those critical numbers. In this case, right here, negative 1, and in this case, over here, the number 2. So I'm going to use the first derivative test. Now, when we chop this number line using these critical numbers, this will give rise to 1, 2, and 3 intervals to test whether it's going to be increasing or decreasing. So the first interval, which is comprised by this part of the number line, will be the interval negative infinity to negative 1. The middle one will be the interval from going from negative 1 to 2. And the last interval will be the interval that goes from 2 to positive infinity. Now we are going to take a test value to determine whether the function increases or decreases, because all we look is at the sign of f prime. The sign of f prime, whether this is positive or negative. So keep in mind that the derivative means slope. So the sign of the derivative is going to be the sign of the slope. If the sign of the derivative is positive, then the slopes are positive, that is increasing. Otherwise, if the derivative is negative, well, then we have a decreasing function at that interval. So in this case, I'm going to choose any value. In this case, I'm going to choose the value negative 2. In this case, in this interval, I'm going to choose the easiest number, which is 0. That'll simplify the calculations a lot. And then I'm going to choose the number 3 over here. Alright, so this is what I do. This is what we do in this case. We are going to evaluate these numbers in the derivative f prime. So I'm going to evaluate below f prime at -2, f prime at 0, and f prime at 3. So I'm going to evaluate the derivative. So that's going to be 6 times number squared minus 6 times number minus 12. 6 times number squared minus 6 times number minus 12. And finally, same. So I'm going to plug in the numbers. -2, 0, and 3. -2, -2, 0, 0, 3, and 3. Ultimately, in this case, I'm not going to care about the number I obtain from plugging in the numbers. The only thing we care is the sign of f prime, not the value, not really the value, because what we want is to get conclusions based on the behavior of the sign. So in this case, I'm going to get 2 squared, which is 4, times 6 is 24, and then 24 negative times a negative is positive 12, 24 plus 12, and then minus 12, which is 24. That is greater than 0. So in this case is positive. Okay. On the other hand, 0 squared, the first two terms are going to zero out, because 0 squared is 0 times 6, that's 0, minus 6 times 0, which is also 0, minus 12, which is a number less than 0, that's negative. Finally, 3 squared, which is 9 times 6, that's 54, and then negative 6 times 3, and minus 12. So I'm going to subtract the negatives. I'm going to add the two negatives, so that's going to be 30. 54 minus 30, that's 24 again, which is also a number greater than 0. That means positive. Okay, conclusion, increasing, decreasing, and increasing again. Alright, so that means it's going upwards, it's increasing, then it's going down, and then it's going up again. Okay, so from this behavior, from going up to going down, here we reach a REL max. We have a REL max. Over here, notice the behavior. We are going to have a REL min, a relative minimum. Alright, now how do we get the points of those relative minimums? Well, all we do is plug in these two numbers in the original function to x cubed minus 3x squared minus 12x. Okay, but ultimately I'm not going to really care about finding those values. All I want is to review the process of using both derivative test to find potential extrema. So let's see. Let's move on to the next page. So in the next page we are going to do the same, but now we are going to use the second derivative test. The second derivative test will tell us whether, or the intervals in which a function is concave up or down, and if we have inflection points, that is points in which we are going to have turning points, when those are the points in which the graph changes the, what's it called, the concavity. Okay, so I'm going to take the second derivative of this function. So we had the function 6x squared minus 6x minus 12. The second derivative, it's going to be 12x minus 6. That's going to be the second derivative. Now, we need critical numbers from the second derivative, which I typically call them second generation critical numbers because they come from the second derivatives. Typically what I do, I call the first derivative critical numbers, or the critical numbers that come from the first derivative, I call them first generation critical numbers. Just so when you take derivative, you don't mix up the numbers with their corresponding derivative. So I'm gonna set the second derivative equal to 0. I'm gonna solve for x. So x equals 6 over 12, x equals 1/2. So that's going to be our critical number. So we are going to slice and dice again our number line, and over here we are going to have our critical number 1/2. This will give rise to two intervals to test, and I already set the table for you with two blank columns to fill in the information for it. Alright, so now let's see. Let's define the intervals. The first interval will be negative infinity to 1/2, and then 1/2 to positive infinity. We're gonna pick a test value in the first interval. The easiest, of course, is always 0, and on the second interval, 1 will be a good test value. What are we going to do now? F prime of x should have seen. So I'm going to evaluate f double prime at 0, and I'm going to evaluate f double prime at 1 to see the behavior of the function in terms of concavity. So 0, 0, 1, 1. Okay, so let's simplify this. So 12 times 0, that's 0 minus 6, this is negative 6, which is a number less than 0. So that means, in this case, when the sign of the second derivative is negative, we have this concave down. I'm going to abbreviate this as C down for a reason. I will show you why. When we evaluate 12 times 1, when we evaluate the second derivative at 1, we get 12 times 1 minus 6, which is positive 6, that is greater than 0. So that's positive, and this is concave up. Alright? Now, so how are we going to find whether we have a point of inflection? Well, this is what I like doing when going over this type of problems. When we have a function concave down, f of x is sad in this interval concave down, and then in the intervals where it's concave up, we have a happy f of x here. So in this case, f of x is changing from sad to happy, so there is a turning point then in between that is called a point of inflection. So in this case, point of inflection at x equals 1/2. Again, I'm not going to care about the y values. Alright, so there is a second part of the derivative, of the second derivative test, but in this case, second derivative test to determine max and min. So wait a minute, hold on. I thought the first derivative test was for max and min, and the second derivative test to find concavity. Are we mixing in we're mixing up the ideas? Not really. We're not really mixing everything up. So all we're doing here is using another second derivative test, in which when we take the second derivative and evaluate it at the critical value, if we get some number less than 0 that is negative, then we have a max, a real max. Otherwise, if the second derivative, oops, no, that's not the notation. That's the notation, double prime. I was going ahead with partial derivative. So when we evaluate the critical number and we get a positive number, we get then a real mean. So keep in mind these ideas are sort of reversed. So second derivative negative means max. Second derivative positive, real mean. And you can see it in the picture in the happiness and sadness of f of x. So in this case we have a negative second derivative. Do you see the sadness? Well, nevertheless, despite the sadness, has the maximum point. It has the maximum point despite the sadness. However, f of x in the interval where it's concave up, rather where it's happy, despite the happiness, look at the behavior. It has the mean. So now we're going to use the second derivative test, but I'm going to evaluate. Oh, by the way, I need to be very precise. C is the critical number from the first derivative, aka the first generation critical number. All right. Now, and so we're going to evaluate f double prime at, what was the critical number for the critical numbers for the previous case, where x equals 2 and x equals -1. Those were the critical numbers. So in this case, critical numbers, because we may have more than one, f double prime at -1. So f double prime at and just plug in the numbers. So 2, 2, and -1, -1. So 12 times 2, that's 24, minus 6, which is 18, which is greater than 0. That means, according to the test, to the theorem here, we are going to have a real mean. And then f of -1. So I'm going to have 12 times -1, which is -12, minus 6, that's going to be -24, which is a number less than 0 or negative number. Well, what do we get? A real max. This should be consistent with what we did in the previous page. Is it? Let's verify that. Okay, let me show you. Let me see if I can overlap the pages. I don't have to scroll. Okay, it's kind of hard to see it. So let's see. So in this case, at positive 2 we had a relative mean. At positive 2 we had a relative mean. At -2 we got a real max. At -2 we got a real max. Alright, so this is the part I'm interested the most, because this idea right here of the second derivative test, this will be extended to the multivariable function idea and the process that we're going to be following. So when I showed you the d-test, and when you see all this double partial, less than 0, real max, and blah blah blah, well, so it doesn't look like you are just looking at a bunch of nonsensical symbols. So we are going to make a huge connection between this second derivative test for max means with the d-test, which is what we do now in the next topic. Alright, so let's find out what we're going to do here. So What we did in the previous pages, well, we found max and mins in 2D in a graph for a function in which whose graph is graphed in the xy plane. What we're going to do here, we are going to find relative maximum, relative minimums in the 3D space, but we are going to introduce a new type of point called saddle points. All right, a very interesting type of point in which in some direction, for example, if you look at this graph, in the y direction we have a minimum, but if we look at the graph in the x direction, we have a relative max. So in a way, it's a max and a min at the same time. Where have you seen that? Well, saddles, of course, that's why they call saddle points, but also who likes Pringle chips? Pringle chips right here, if you look at them in the cross-sectional point of view, you are going to see a maximum point over here. So here we're going to go up the hill, reach a max, and then go down. But when you look at it sideways, in this case we are going to have a relative minimum. That's exactly a saddle point. This is good stuff. Now, how are we going to find critical points for functions of the variables? Well, when we had the single variable function, first we took the first derivative and then we set it equal to 0 to find all critical points, right? Like in this case, we got to critical points. In this case, for functions in which we have more than one variable, we are going to take the partial derivative with respect x and the partial derivative with respect y, and then set both equal to 0. So it's not just going to be the derivative with respect x equal to 0. It's going to be also the derivative with respect y with respect, with the partial derivative with respect y, and set it equal to 0, and then this will give rise to a system of equations to solve. Yes, those are going to be a lot of fun. All right, so now the criteria, the definition here, or the theorem if you will. So if you look at this box, well, it has a lot of letters, symbols, ideas. Well, so once we find those critical numbers, we are going to move ahead and take a second partial with respect x and second partial with respect y, and we will require to find the second partial first. Well, the first partial with respect x and then the second partial with respect y. And then this is the criteria. We are going to compare again the connection I wanted you to make from the previous topic, from here. Second derivative less than 0, relative max. Second derivative greater than 0, relative min. What do we have? We are going to have a relative minimum if, well, d greater than 0. For now, don't look at d. However, the second partial is positive, relative minimum. The second partial is negative, relative max. If the quantity d, which we will evaluate, is a negative number, we are going to have a saddle point. And the test will go inconclusive if d turns out being 0. Well, we don't get this very often. Okay. Alright, let's see what's next. I think the next thing is going over an example. So let's see an example. Alright, so let's find relative extreme values of f of x, y equals x squared plus y squared. Alright, without doing any calculus, any computations, well, in some cases it's not easy to predict, because in this case the reason why it's easy is because the function is a simple one. For functions like example 2, well, there's no way we can get a graph of it. But for example, here I'm going to draw in 3D. You don't have to do this for every single problem. I'm doing this just so in a way I can predict what I'm going to obtain. Okay, so suppose this is z equals x squared plus y squared, because I mean typically x squared, when we have a function that depends on x and y, the input is an order pair, the output will be a number, which in this case is graphed in the z coordinate, in the direction of the variable z. Alright, now I'm going to pretend I don't have this y squared. So what do I have here then? Does that look familiar at all for you? I believe if you say something like y equals x squared, which is a parabola, well, then you are correct. But in this case, it's not y, is z in this case, in the direction of x. Let me actually extrapolate a little bit with dash line. And then what are we going to obtain? So we are going to obtain a parabola in the direction of x. Now I'm going to pretend I don't have this y squared. I mean the x squared. I'm going to have z equals y squared. So now I'm going to draw a parabola in the direction of the y variable. So what are we going to have here? What are we going to have here? Well, drawing graphs in 3D is not my forte here, but if you look at this, this looks like a paraboloid. This looks like a paraboloid. It's basically a solid generated by two parabolas going getting drawn into different directions. But the main takeaway here is, look at this point right here. It's going to be a minimum. Now we are going to do the algebraic process to determine, well, the calculus and algebraic process to get this conclusion. Alright, let's begin by taking the first two partial derivatives of this function. So fx rather, just x, not the double yet. The first partial with respect x will be 2x. And the first partial with respect y equals 2y. Now I'm going to create a system of equations, 2x, 2y, and set them equal to 0, each of them. So in this case, these two equations are going to be really easy to solve. So all we need is to divide both sides in each equation. That means x equals 0 and y equals 0. So we have the critical point. Notice in this case, I'm not calling these critical numbers the same way we did it in the single variable function, right? In this case, I call this the critical numbers because they were just numbers. In this case, I'm dealing with an ordered pair. That's why I will call it critical point. Okay, so the critical point is the origin in this case. Well, so far we are consistent with our picture here, aren't we? Alright, so now that we found the critical point, the next step is to find the second partial, fxx, which in this case the second partial derivative, it's going to be 2 with respect x. The second partial derivative with respect y, both of them, y equals 2. And then I need a third one, which is first with respect x, which is 2x, and then with respect y. But the derivative of 2x with respect y will be 0. Okay, so from here I'm going to form the quantity d, which is formed by multiplying fxx, fyy minus fxy. Now, if you're wondering where is this formula coming from, well, don't worry, let's just use it. Where it's coming from, it's a very painful process, a very painful algebraic process with functions of two variables. However, in this case, the idea is just to know how to use this, how to use this process, how to use this the test. Okay, so in this case, what are we going to have? Fxx, which is 2, fyy, which is also 2, minus fxy, which is 0, quantity squared. That's going to give us d equals 4. Okay, so in this case, if we had x's and y's remaining, we would have plugged in x equals 0 wherever it corresponds and y equals 0 wherever it corresponds. But in this case, in this very simple problem, in this simple exercise example, there's no x's and y's involved, but we will have some of those in the future exercises. All right, so in this case, we notice that d is a number greater than 0 because it's positive, and also we notice that fxx, the second derivative with respect x, is also a positive number. So at the end, that is what we look for. We look at the sign of d and the sign of the second partial derivative with respect x at the given point, at the given critical point. Now, having these two conditions together, we conclude that d positive, d greater than 0, and second partial greater than 0, relative minimum. Okay, so the point 0, 0 is a rel min. Now, do you see anything inconsistent with the picture I got here? Notice how everything is consistent. Well, again, in future exercises, we are not going to do this drawing. I just wanted to make a quick connection between the geometric way and the analytic way. So from now on, we're going to do everything the analytical way. So let's look at another example. We're going to find the relative extreme values of f of x, y equals 3x squared minus 4xy plus 4y squared minus 4x plus 8y plus 4. First thing we do, take the first partial derivative with respect to x. That'll be 6x. And then minus 4y. And then over here, the derivative of 4x is negative, of negative 4x is negative 4. Everything else, like x, y, and the y squared, are considered constant. So, next thing we do is find the partial derivative with respect to y. So in this case, this term goes to 0. The derivative of the second term will be negative 4x. It's going to be 0 minus plus 8 plus 8y, and then plus 8. So those are going to be our two first partial derivatives of the function. So now I'm going to create a system with 6x minus 4y minus 4 and set it equal to 0 simultaneously with the first partial derivative with respect y, which is going to be negative 4x plus 8y plus 8. That equal the 0. Now, in this case, we're going to have a system of equations with two equations and two unknowns. Keep in mind that there's a good number of methods to solve systems of equations. such as elimination, substitution, matrices, calculator RREF, what else? Determinants, the Cramer rule. Well, at least 5 methods to solve these systems of equations. So in this case, I'm going to use, you could use the method you prefer. It's up to you. However, I'm going to use elimination. I'm going to use elimination because in this case, if you look at the y's, if we multiply the first equation by 2, the system of equation becomes 12x minus 8y minus 8 equals 2 times 0, that's also 0. The second equation remains the same. Alright, and in this case we are ready to eliminate the variables here. Alright, so combining the equations will eliminate the y's. That's why we call it elimination, the method of elimination. So 12x minus 4x, that's going to give us 8x. But in this case, something funny occurs as well because the 8's go away as well. So this will be equal to 0 and x equals to 0. So far we have a critical point in which the x-coordinate will be a 0. Now we need to find the y-coordinate. So from here we go to any of these two equations, plug in x equals to 0 and solve for y. So I'm going to use the first equation just because, why not? So 6 times minus 4y minus 4 equals 0. So over here I'm going to plug in this x equals 0, okay, to find the y-coordinate of the critical point. And then, well, we're at 6 times 0 is going to 0 out. I'm going to get negative 4y minus 4 equals to 0. Moving the negative 4 to the right hand side, we get negative 4y equals 4, and divide both sides by negative 4. We get y equals to negative 1. So our critical point is going to be x equals 0, y equals to negative 1, which we need to test. We need to test whether the critical point will be a minimum or a maximum or a saddle point. We will find out. What else do we need? We need the second derivative, the second partial with respect x. So we start from the first derivative, which we already got, take the second, the derivative, the partial derivative of 6x with respect x will be 6. The partial derivative of these two terms with respect y will be 0, so this is just 6. Now the second partial derivative with respect y is going to be, well, let's go over here. The derivative of the first and the third are going to be 0 because we are differentiating with respect to y, but the derivative of the middle term will be 8. The derivative of x first and then y will be negative 4. So we are going to look at the d quantity, which is fxx times fy, y minus fxy quantity squared. Alright, so it is going to be, well, f double x is equal to 6 times f double y equals to 8, and then minus the quantity negative 4 squared. So we're going to get 48 minus 16, which equals the number 32. So in this case, we are going to look at two conclusions. Number one, D is a positive number, positive 32, that is the greater than 0. And also fxx is, which is 6, is greater than 0 also. Again, let's look at criteria at the test. Both positives, d positive and fxx evaluated at the critical point greater than 0, we get, again, a relative minimum. So 0, negative 1 is a rel min. Okay, so that's what we get. All right, let's look at another example on the next page. So find the relative extreme values of f of x, y equals 4y squared plus x squared minus 12y squared minus 36y plus 2. Alright, let's have a look at that example. So number 1, find the first partial derivative with respect x, that's 12. Oh wait, not a minute, wait a minute, it's 2x. I was looking at the y's for some reason. So with respect x, this term is 0, this term is 0, all terms right here is 0, we only remain with 2x, that's about it. With respect y, the derivative is going to be, now that's the 12y squared minus 24y minus 36. Okay, so we are going to create a system of simultaneous equations with this guy set it equal to 0 and that other guy set it equal to 0. So 2x equals to 0 and 12y squared minus 24y minus 36 equals to 0. So from here, we obtain that x equals to 0 because all you need to do here is divide both sides by 2 and all we get is x equals to 0. Okay, now we need to find y. Well, in this case, unlike the previous example, notice the two equations had variables in common. So in this case, we had a pair of independent equations. By independent, I mean that one of them depends on one variable, the other one depends on another variable. So I'm going to worry about solving the equation below. Okay, so, and to do that, I'm going to divide both sides by 12 because all numbers are divisible by 12. I mean, you don't want to do the factoring of this equation. You don't want to solve this equation by factoring using these huge numbers. Like multiply 12 times negative 6 and then whatever huge number you get, factors of those numbers that add up to negative 24, which in this case I think it's kind of straightforward, but I think I don't want to do that. So I'm gonna write a simpler equation. So that's gonna be y squared minus 2y minus 3 equals to 0. And I'm going to look for factors of negative 3 that add up to negative 2. In this case, y plus 1 times y minus 3 equals to 0. Using the zero product property, we get that y equals to negative 1 and y equals to 3. So in this case, we are going to obtain two y values. So what are we going to obtain? We are going to get two critical points. Two critical points in this case. Number one will be 0, negative 1, and the other one will be 0, 3. Okay. Now we need to test those points whether They are relative min, relative max, or Pringles chips, aka saddle points. In this case, I need 3 more partial derivatives. In this case, the second partial with double x. So the derivative, we already found the first derivative with respect to x. We got to x. The second derivative will be 2. And then we need the second partial twice y. In this case, we already had the first one. Let's find the second partial derivative with respect to y, which in this case is going to be 24y minus 24. All right, which I will simplify, like I'm going to factor out the 24 to make calculations easier in the next step. And then I need a third partial derivative, which is first with respect x and then with respect y. So the derivative that we already, so we got the function. Take the first derivative with respect to x, we get to x. Now we take the derivative of this function with respect to y, but in this case it depends on all x, so this will be 0. So now let's evaluate the quantity d, which is fxx times fyy minus fxy quantity squared. Alright, so let's substitute the quantities. Fxx, we got that it is number 2, times fyy, which is 24, y minus 1. And in this case, subtract the square of the derivative, the sequence xy, which in this case is 0 squared. So that's going to give us d equals 48y minus 1. So we are going to use an expression here. Unlike the previous examples, if you look at the examples, well, the d's were simpler, were just straight numbers in this case. And all we did is look at the sign of it. Same here, this simple d gave us a number, right? In this case, greater than 0. That's what told us it was a minimum. Well, in comparison with f double x being positive. Now, in this case, we are going to obtain a d in the form of an algebraic expression. So we are going to use this number 1 to test the point 0, -1. So in this case, I'm going to plug in d equals 48. So in this case, I'm going to plug in the number -1 over here. So -1 minus 1, that's going to give us 48 times -2, which is -48. So what do we got? A negative number. All right, we got a negative number here. All right, let's do the same to test the point, the other critical point, which is 0, 3. So I'm going to plug in this 3 here where it corresponds in the letter y. So in this case, if our d had x's and y's, we would plug in whatever number, in this case 0, and plug it in there. But in this case, there's no x's. Okay, there's only y, so that's why we just plug in that number there. So d is equal to 48 times 3 minus 1, which equals 48 times 2, which equals 96. By the way, I made a silly mistake here, not -48. This should have been -96. Okay, negative 96. Now in this case it's positive number that's greater than 0. Okay, let's make conclusion. So in this case D is less than 0. What do we conclude when D is less than 0? Okay, so in this case we have Pringles chips. Saddle point, a point in which a max and a min occur simultaneously depending on the direction. In the direction of the cross-sectional for the Pringles chips, it's a max, but in the transversal point of view, we can see this is a minimum. It's a minimum point. So saddle point at the point 0, negative 1. What else do we have? What about the test for 3? So in this case, we have D greater than 0, but in this case, when D is a positive number, we need to look at the sign of the second partial derivative, which in this case is positive. What happens when they are both positives? The first one, a minimum. So rel min at 0, 3. Okay, so we finished this exercise. Let's look at another example. And the next one is gonna be a very interesting one. It's going to be a little bit more involved with calculus and writing expressions. So we are gonna look at the case in which f of xy is an exponential function. All right, so first partial, it's going to be itself when it comes to the derivative of an exponential function, and then times the derivative of whatever it's on the exponent with respect, in this case, with x. So in this case, 2x. So we're using a mini chain rule there. Okay, and then I will actually set it equal to 0, so I don't have to write it again. I'm going to use curly braces at this point, so I can save space. That equals to itself, but times the derivative of the exponent with respect to y. In this case, negative 2y. Looks like an r, this is a y. Okay, 2y. Alright, we're going to set this equal to 0. Okay, we need to solve this system. So number one, let's highlight all we need to solve. So first of all, I need to set the 2x equal to 0. I need to set the negative 2y equal to 0, and I'm going to use purple for the exponential function. I need to set that equal to 0. Set it equal to 0. In this case, I'm highlighting with the same color because it's the same factor. So 2x equals to 0, no big deal, x equals 0. Negative 2y equal to 0, I guess no big deal, y equals to 0. But the problem here is with the exponential function. Okay, one thing you need to keep in mind, in this case there will be absolutely no critical values from the exponential function, because exponentials never go to 0. Okay. I mean, let's illustrate this in a different way. Well, that's one idea. The other idea is, well, e to the x squared minus y squared equals 0. Take ln to both sides to get rid of the exponential. That's valid. However, we are going to get x squared minus y squared equals ln of 0. And if you try to evaluate ln of 0, well, one way to view this is it is undefined, but the actual well, it is undefined. Yes, it is undefined. However, from the point of view of limit, well, in this case we would be approaching 0 from the right, and we would get to negative infinity again. Keep in mind, recall that the graph of f of x equals ln x. The graph has a vertical asymptote at x equals 0, and it looks like this. That is, approaching 0 from the right is going to go to negative infinity. Alright, so in this case, the critical point is going to be no other than the origin, 0, 0. Alright, so now that we know the critical point, we need to test. We need to use the d-test, which involves second partial derivatives. Alright, so here is the part that it's going to be a lot of fun. We are going to use the product rule with partial derivatives a few times here. Alright, so number one, let's recall what the product rule is. So the derivative of a product uv is u prime v plus v prime u. Okay, so that's the rule that we need to recall here. And in this case, this is going to be our u, and the exponential will be our v. For the second function, that'll be our u as well, the negative 2y, and the exponential part will be the v. Alright, let's have fun with this product rule, problem. So fxx, that is the second partial with respect x. So the partial derivative with respect x of the first factor, which is u. In this case, the derivative of 2x is going to be 2 times v without doing anything, plus the derivative of the second, which in this case, well, again, the derivative of the exponential, times, well, in this case involves a chain rule, 2x, but in this case times u, which is 2x as well. Okay, what did I do here? So this is u prime v, and then all this is v prime u. Okay, that's the product rule for the first partial to get the second partial. Now, let's simplify this. So this is going to be simply 2e to the x squared minus y squared, and then 2x times itself is going to give us, and I'm going to write it in the front of the exponential, 4x squared e to the x squared minus y squared. Okay, I'm going to write this in a simpler way, and we better do that because when we have a huge expression like this times another one with respect to y, you might want to have this in terms of a simpler function. So what am I going to do? I'm going to factor the GCF. To factor the GCF, which is 2e to the x squared minus y squared, and then that times 1 plus 2x squared. Okay, I'm going to repeat this whole process again, but now with the second, with the partial with respect to y. Okay, so that's so far one. So let me use a different color to box this. Okay, now f double y equals to, okay, it's going to be the derivative of the first, which is then the derivative of negative 2y, which is negative 2 times itself, the second factor, e to the x squared minus y squared, plus the derivative of the second factor, which is itself first of all, times, well, we do a mini chain rule on this, which is going to be negative 2x, and then times the, no, not negative 2x, negative 2y rather, negative 2y, and then times the negative 2y from the other factor. Again, let me denote everything I did in terms of the product rule that we have here. Okay, so this is u prime, and this is v. Then this is v prime, the derivative of the second, times just u, which is simply negative 2y. In just the same way, I will simplify this to negative 2e to the x squared minus y squared, and then negative times a negative is positive, 2y squared, 4y squared e to the x squared minus y squared. Which again, just the same way I did it with the previous one, I'm going to factor out the GCF, which will be, in this case, this is going to be negative 2e to the x squared minus y squared times, well, I'm going to use a bracket this time, bracket, and this is going to be 1 minus 2y squared. Okay, minus 2y squared, and that's about it. So we need one more derivative, the partial. Well, let me box this one first. This will be with respect x first, and then with respect y. So let's look at the derivative with respect x. So in this case we are going to take this with respect to y, but in this case we are not going to need the product rule, because in this case this 2x, which indeed is multiplying, there's a product, however depends on x, and we want to take the derivative with respect to y. So the derivative of some exponential function times a constant is itself times negative 2y, which in this case this reduces to negative 4xy times e to the x squared minus y squared. Okay, which I will box as well. Okay, now we have all the information to form our D. Okay, so D, which is fxx times fyy minus fxy quantity squared. Okay, how are we going to do that? Okay, this big chunk right here, I'm gonna copy it. Times 1 plus 2x squared, and then times fyy, which is this whole chunk. However, I don't want to write too many parentheses here because of this negative. This negative, I'm gonna skip it for now. 2e to the x squared minus y squared times 1 minus 2y squared. And this negative, I will just put it in the very front. And then minus this quantity, this guy right here, negative 4xy e to the x squared minus y squared. The whole quantity, keep in mind that this is squared. Oh wow, look at this. Look at this D expression. Remember the first example? Let's recall the first example. Look at this baby example, example 1. fxx, fyy, and fxy were simply numbers back then, even in the second problem as well. However, in more involved situations like this problem, we are gonna get finally a huge expression that in which we will see the x's and the y's going on at the same time. So this example, the reason why I like it is because when after you have looked the easier examples, you look at this one and now you see how everything, when we test the critical number, which in this case 0, 0, well, thank God we're not testing more points. That's the only critical point. Alright, isn't it good? After all the work that we do, well, we are only testing 1 point. So D will be, okay, wherever you see the letter X and Y's actually are going to be 0, but be careful when plugging in. If I were you, I would write every single step. So negative 2 e to the 0 squared minus y squared, minus 0 squared, times 1 plus 2 times 0 squared times 2 e to the 0 squared minus 0 squared times 1 minus 2 times 0 squared minus negative 4 times xy, which is 0, 0, e to the 0 squared minus y squared minus 0 squared. That's, again, I wrote y. The whole thing squared. Okay, so the good news here is that you don't have to worry about this term, because 0 times 0 is 0 times negative 4 is 0 times anything, it's still 0 squared, it's also 0. And whatever quantity minus 0 is going to be our whatever quantity. Now, over here we are going to get, I'm going to simplify this step by step. So negative 2, so this is going to be 0 squared minus 0 squared, which will be simply e to the 0. And then this will be 1 plus 0 squared, which is 0 times 2, that's 1 plus 0. And then same here, times 2, which is e to the 0 squared, which is 0 minus 0, it's also 0. And then 1 minus 2 0 squared, so 0 squared again is 0 times 2 is 0. And we are almost done with this calculation. So D will be, okay, keep in mind that e to the 0, this is 1, this is also 1. So we are going to get negative 2 times 1. 1 minus 0 is also 1 times 2 e to the 0, which is 1, and then 1 minus 0, which is also 1. Multiply all these numbers, we get that D equals negative 4. So in this case, D is a negative number. We don't need to look at the second partial derivative with respect to x, because when we have this situation, what do we have? Another Pringles chips. Saddle point. Saddle point at this for this one. Alright, so this is the last example in which we do find max and mins for a function f of x. Now I'm gonna do one application, one very cool application in which we are going to find the point that we are going to find the maximum point. So in this case, we we are in a situation in which a company produces two different products. In a very generic form, let's call them A and B. Let's call them simply A and B. Okay, and of course, each product is going to have its own price. Okay, because I mean, in this case, we're consider that the two products are different and they both have different products. And in this case, these prices are functions of x and y respectively, where x and y are the number of units sold of each function, of each article, rather, of each thing. So now, when it comes to the manufacturing of a product, there are two main important points right here. Number one, the cost that it takes to manufacture whatever product, and the revenue obtained when selling those products in the market. So the profit of the company will be the difference between the revenue and the cost. All right, for example, in a very simplistic way, suppose you sell sodas for I don't know, for a fundraiser. You buy the sodas. Each soda, the price of each soda is 50 cents. Right? I'm talking about one of those small cans. So it's 50 cents. But in this case, you are going to sell those sodas in your fundraiser for $1.50, let's say. In this case, when selling them for a larger price, you will be making revenue. But in this case, to find the profit, the money that you will get out of it, that is, you need to subtract the original cost. In this case, the number of sodas that were sold from the original price. Okay, now in this case, we are going to have a situation in which the profit, okay, so in this case, the profit will be X number of units of the first product times its price, plus Y number of products of the other article times their price. And then we are going to subtract the cost, which in this case we are going to deal with functions that depend on two variables. So let's look at this example. So Universal Motors makes compact cars and mid-sized cars. The price function for compact cars is P, which is a function of X, the number of cars that are manufactured. P equals 17 minus 2X. And for under certain restrictions, in this case, because if you plug in X equals negative 8, well, you're going to get a negative number. So, and the price function for mid-sized cars is Q equals to 20 minus Y. So both are in thousands of dollars, and again, X and Y are the numbers of compact and mid-sized car respectively. All right. Now, the company's cost function is all this. It's this function in thousands of dollars. Now, the questions are: number one, how many of each car should be produced and what the prices should be, the prices of each, in order to maximize the profits. Also, find the maximum profit. Okay? Find the maximum profit. Let's see. So in this case, let's use this formula right here, P of X, Y. So I'm going to keep it like here, like this. So P of X, Y, which is the function P of X, which is 17 minus 2X, times X. plus the function q of y, which is the price of the other card, which is the mid-sized cards, which is 20 minus y times y. So that's the revenue part. This whole thing is r of x, y. The revenue, and then we're going to subtract the cost function. But be careful here when subtracting the cost function. This whole thing, which is going to be here, all right? So in this case, we need to you don't trust me, you don't want to do calculus on this function. Here we are going to spend about 5 or 6 steps simplifying this function. So number one, I'm going to distribute the x, distribute the y, and then distribute the negative sign. Let's do all those operations. So the profit function, for which we are going to do some calculus, well, a lot of calculus, not just a bit. Well, actually, you will see when we get to the calculus part, it's going to be really easy. I guess the most time consuming step is going to be this simplification of this 17x minus 2x squared plus 20y minus y squared minus 15x minus 16y plus 2xy minus 5. We're almost there. We're almost there as far as simplifying this. All right. I'm going to combine like terms. In this case, the like terms that I see are this x's with this x's, and then this y's with this y's. So those are the only like terms. So let's go ahead and simplify them. So negative 2x. I'm going to write them in descending order of powers in alphabetic order. Minus y squared. And then 17x minus 15x. That's going to give us 2x. 20y minus 16y. That's going to give us 4y. And then 2xy and minus 5. Alright, so that's the simplest way we can deal with this function. So at the end, well, there were just 3 steps. Never mind. Alright, let's look at this function and determine what are we going to get. Well, in this case, they want us to maximize the profit. Okay, how can we tell from looking at this function? So in this case, I'm going to focus on the 2 leading terms. So these linear terms, well, this is another quadratic term, but I'm not gonna look at those terms. Okay, again, let's use the same trick. Pretend I don't have this. I just have the negative 2x squared. Do you see it's an upside down parabola? Also, pretend you don't have this 2x. Do you see the negative y squared? It's also an upside down parabola. So it's, in a way, it's going to be an upside down paraboloid, if you will. All right, but in this case, so having an upside down paraboloid, it's going to give us a maximum, which is, so far, that's looking good. Okay, so far so good. Now let's do the calculus part. Let's find the first partial derivative with respect to x. That's a negative 4x. And then the partial derivative, let's set it equal to 0 at once. And then p sub y, which is negative 2y. Set that equal to 0. Again, in this case, it's not going to be a big deal to... Oh, wait a minute. No. I'm missing a lot of the stuff here. Never mind. Let's see. We're not... I was I was not looking at the other terms. Alright, so negative 2x, that's negative 4x, and then the derivative of 2x is 2, and then the derivative of this term is 0 with respect to x, and then the derivative of this will be 2x with respect x. Wait, not to x, to y. To y. Beg your pardon here. And the derivative of a constant of a number is, which is a constant, is 0. So in this case, negative 2y, these two terms go to 0, plus 4, and then the derivative of 2xy with respect to y is 2x. And in this case, I'm going to set this equal to 0. Alright, the next thing I would like to do is rewrite the system in alphabetic order, because notice x, y, y, x, well, we prefer to write this using equations that are written in alphabetic order. So negative 4x plus 2y plus 2. 2x minus 2y plus 4. And the reason why I'd rather do this is because you will see the beauty of this. In this case, we don't need to multiply any of the equations by any non-zero constant to eliminate one of the variables, because the y's are already in the form to cancel each other. Plus 2y minus 2y. So negative 4x plus 2x, that's a negative 2x. 2 plus 4 equals 6 equals 0. And then if we solve this mini equation, we obtain negative 2x equals negative 6, which gives us x equals 3. So far, this has to be good, because if you get a negative number, then you are talking about a negative number of cars, which in this case, well, in the context of that, that'll be a loss of cars. Maybe someone stole, someone made a robbery in the manufacturer place. All right, but in this case, it's not the case, because we are for sure getting a maximum profit, so that cannot be from loss of assets, of course. All right, so I'm gonna use this x equals to 3 and plug it in any of these equations. So I'm going to use the first equation, negative 4 times 3 plus 2y plus 2 equals to 0. That's going to be negative 12 plus 2y plus 2 equals 0. Combining like terms here, we get 2y minus 10. Oops, minus 10. Let me erase this and make it a minus. Equals to 0, so 2y equals to 10 and y equals to 5. Again, so far so good. Positive numbers of cars to manufacture, of each mid-sized and compact. Alright, so what do we have? Critical point (3, 5). What are we going to do? We are going to use the d-test to test this point, but we need the second partial with respect to x. So the first partial was negative 4x plus 2 plus 2y. These two terms zero out, and I get negative 4. P double y is here. It's the first partial with respect to y. Then these two terms go away. We get negative 2. And then p with respect x, which is negative 4x plus 2 plus 2y. But now with respect to y, which in this case is 2. All right. So now we are going to build the D expression f, or rather p. In this case, it's not f, it's p. Pxx, pyy minus pxy quantity squared. So let's plug in the numbers. So negative 4 times negative 2 minus 2 squared. So negative 4 times negative 2, that's a positive 8. All right. And 8 minus 2 squared, which is 4, that equals to 4. All right. So now let's find the conclusion, the grand finale. Well, almost there. We're almost there. So in this case, we have the D is positive, and we need to find P double X. Otherwise, again, if D is negative, then we don't care about the sign of the second derivative, because in that case, we already know that it is a saddle point, a Pringles chip in this case. So in this case, these are both positive. What are we going to get? Wait a minute, no, this is negative. Hold on, this is negative, because otherwise I don't get the right conclusion. This is negative, and what do we conclude when we have D positive and the second partial to be negative? In this case, relative maximum. Alright, now we need to find that maximum profit. To find the maximum profit, well, let me actually use a separate piece of paper here. So to find the maximum profit, you might want to use the back side of your page in the case you printed these PDF files. Otherwise, if you're using your notebook, just carry on. P of 3 comma 5. So I'm going to plug in this in the profit function, which is this function right here, that better box. So I'm gonna go ahead and plug in the numbers within this function. So this is negative 2 times x squared, which is 3 squared, minus y squared, which is 5 squared, plus 2 times 3 plus 4 times y, which is 5, plus 2 times 3 times 5, and minus 5. Okay. In this case, if you use a calculator to this, you are going to get P of 3 comma 5 equals to 8. Okay, but in this case, the profit, let's now put context to this. In order to put context to this, so keep in mind that the profit function, where's the profit, is in thousands of dollars. So that means okay, let's write a brief paragraph here, so to have a good interpretation. The maximum profit is obtained or reached when selling let's go back to the critical point. The critical point, which is 3,5, 3 cars, actually 3 compact cars, and 5 mid-sized. Okay. Such maximum profit. Okay, keep in mind that this is not, well, it's not going to be $8. Come on, I mean, think about selling cars. If you are making a profit of just $8 by selling all and manufacturing all these cars, well, that's not a good business. So that's why they're telling us that uh, this profit is in thousands of dollars. So in this case, thousands of dollars. All right. Now let's look. There's another part to a last part for this. They're also asking us for the prices, how many of each in the prices. Okay, so now we're gonna go back to the price functions, in which the price function is gonna be price when each compact car is sold for, okay, let me leave a blank here, and each mid-sized car is sold for blank. Okay, I'm going to calculate the prices, which in this case, price for compact cars versus price for mid-sized cars. So in this case, we're going to go back to these functions P and Q, where P equals 17 minus 2x, 17 minus 2x, which in this case x equals 3, 17 minus 6, so P is 11. Okay, and on the other hand, Q, which is the price for mid-sized cars, that's a 20 minus y, 20 minus y, which in this case is 5, that's Q equals 15. But 15, again, these prices are in thousands of dollars. So each compact car is sold for $11,000, and each mid-sized car is sold for 15 at a price of 15,000. So this is the interpretation right here. The maximum profit obtained when selling 3 compact cars and 5 mid-sized cars. And such max profit is $8,000 when each compact car is sold for $11,000 and each mid-sized car is sold for $15,000. Alright, so we wrap up this section with this word problem. Well, I will see you on the next video.